So we need to turn more than 2 solar masses into energy to power one of these things. I mean, that's pretty extreme, but you know, it's possible, isn't it?
Well, it is. For example, when a supernova occurs, you expect about almost 2 solar masses of stuff, especially in the really large ones, to be converted, the gravitational energy to be converted into energy. But there's a problem, because when these explosions happen, these supernova explosions happen, most of the energy, as the supernova collapses, comes out in neutrinos. And indeed, 99.9% of the energy comes out in neutrinos. Remember, neutrinos can travel right through the stars, so they just go out and really don't do anything.
So if 99.9% of the energy is in neutrinos, only 1 part in 1,000 could be coming out in gamma rays. So if we've got energy equivalent to 2.7 solar masses in gamma rays, you've got to multiply that by 1,000 to get total energy. So that's your 2,700 solar masses. Now, no.
Right, so this is, but on the other hand, you know, we do see them, so they do exist. We know how bright they are, so it's a bit of a mystery.
Well, maybe what's going wrong is how we work out the luminosity. Because, of course, what we measure is the flux of gamma rays per second picked up by our satellites or whatever, and we're therefore working out the luminosity using the equation flux equals luminosity over 4 pi d squared with the distance.
Yep.
But if you remember how we calculated that, what we were doing was assuming that when something emits radiation, it emits radiation in all directions. So the radiation is spread uniformly over a sphere, and the sphere has area of 4 pi d squared, and so the amount of flux we pick up is the luminosity divided by the area of that whole sphere. But what if, instead of shining in all directions, this thing was somehow like a searchlight beaming the light directly at us? In that case, instead of flux equals luminosity over 4 pi d squared, if it's beamed into only like 1% of a sphere, it would be luminosity over 1% of 4 pi d squared. I mean, that might help save us from this immense luminosity, which seems just impossible.
Well, that's a good point, because it turns out that when, you know, a supernova collapses, if there's going to conserve angular momentum, it'll start spinning. It has a magnetic field. You can imagine the whole thing collapsing down and shooting jets out. We see these jets, for example, in quasars.
As we talked about earlier, we see them in protoplanetary disks. So it seems to be a fairly common phenomenon when you get something rotating with magnetic fields that you get jets. But how's that going to help you? I mean, you've got a quasar, it's got stuff coming out as jets, but you can see the jets from any angle. The radiation, even though the jets are coming out in a particular direction, the radiation's coming out in all directions.
Yeah, so you're right, that if this was just a jet coming out and we just had essentially a light coming out in all directions, nothing helps. It even makes it worse, because all the energy has to be concentrated in a tiny little spot.
So you've still got your flux equals L over 4 pi d squared, and that still gives you the luminosity that's just ridiculous.
But we do have a trick. And the trick is, we think this jet might be going really, really fast. And so let's just consider if I'm out throwing something. Let's just say we're going to use a Newtonian analogy. We're not going to use light. What I'm going to do is I'm just going to say I'm putting things out in all directions. I'm, you know, for example, putting out light and not worrying about the effects of relativity.
Well, let's say you're standing on a cart and throwing balls or money in every direction, yes.
And imagine that I now am moving. So I add a vector of velocity. And so by how we add velocities, we just add that vector to each of these.
So you're sitting on your cart and you think you're throwing money out that way.
Yep.
But of course, because the cart's moving, from your point of view, your frame of reference, it's going like this. But from my point of view, as say the person pulling the cart along, it's actually going add this to that in this direction.
That's right. So if we take all those and add all those vectors together, as we say, if I'm moving forward, I'm actually end up looking, my pattern's going to look like that. And you can see, instead of being spread out over all directions, it's actually concentrated in the forward direction.
Okay, so from your point of view, you're throwing things in all directions, but from my point of view, as I'm pulling you along, it looks like, because you throw things out sideways, but you're moving forward at the same time, it actually is all moving forward. So it looks like you're beaming or you're throwing things in a forward direction. Well, that's sounding a bit better.
This can help us. And it turns out that if we employ relativity, which we're not going to do right now, stay tuned for later in one of our other courses where we will actually calculate within the violent universe how this works in a relativistic sense. you can really magnify the beaming. And indeed, one of Einstein's things that he calculated when he developed special relativity was the formula for how light is beamed for something that's moving forward. So
what it's telling you is there's an angle into which nearly all the radiation is beamed. So instead of going in all directions, it's going in just this angle here, angle theta, which is the angle in there. And that's given by the square root of 1 minus velocity divided by the speed of light squared. So if your velocity is much less than the speed of light, like me running along here, then the light's going in pretty much every angle. But if I was running here at best part of the speed of light, v over c is close to 1, therefore v over c squared is close to 1, so that's giving you a pretty small angle.
So let's go through and calculate exactly what angle we need to save ourselves.
So what angle do we need to save us? Well, we know the angle is given by this equation. When we worked out the original inverse square law, we assumed that a source would send its radiation uniformly over an entire sphere of radius d, say. But now, because of this beaming, it's instead going to send all its radiation into a cone. Let's call that length there r. So what this means is over most of the sphere the radiation is nothing. It's all concentrated into here. So the concentration is going to be by the factor of this area compared to the whole area of the sphere. Now that angle here is theta. We know from small angle approximation that r is approximately equal to d theta, as long as theta is measured in radians, and this equation up here is in radians. So the area here is simply pi r squared, which is d theta squared, whereas the area of the whole sphere is 4 pi r squared, or 4 pi d squared in this case. 4 pi d squared. So that ratio is pi's cancel, d squareds cancel, equals theta squared over 4. So that is telling you the ratio of areas. The ratio of fluxes is going to be the reciprocal of that. What it means is if you're concentrating all the radiation into an area that's only 1% as big, that means that the energy you get inside that area is going to be 1 over 1% or 100 times bigger. So the amplification is going to be 4 over theta squared. Now what do we need? Our calculations suggested that using up 2 solar masses might be okay. The thing that killed it was the extra factor of 1,000 or so, due to the fact that most of the radiation comes out in the form of neutrinos. So if we can bring the luminosity down by a factor of 1,000, that starts making it plausible. So what we want is an amplification factor of about 1,000. You bet it would be more, but that will bring everything down to reasonable proportions. So 1,000 gives you 4 over theta squared, which gives you a theta of root 4 over 1,000, which is 0.06, which is about, if you convert from radians into degrees by multiplying by 180 over pi, it's about 4 degrees. So that's a narrow but not ridiculous angle. What sort of speeds do you need to make it happen? So if we've got 0.06 equals root 1 minus v on c squared, square both sides, rearrange, and you end up with v on c equals root 1 minus 0.06 squared, which is 0.998. So to get this to work, we have to have stuff coming out at 0.998 at the speed of light, very, very close to the speed